And I'm introducing the next speaker. Piotr Wyrwiński is a graduate student at Poznań University of Technology and also a member of our group. Currently, he works in Poznań Supercomputing and Networking Center as a machine learning researcher. So he will be talking about malware classification. So Piotr, the floor is yours, at least virtual floor.
Hello everyone, welcome to my talk. The topic for today is attention-based approach to malware classification. My name is Piotr Wyrwiński. I'm a student of computer science at Poznań University of Technology, and I'm a proud member of GHOST, currently working at Poznań Supercomputing and Networking Center. Let's begin. The agenda for today is first, I will talk about the competition from which we obtain the dataset. Next, I will cover the topic of using attention mechanism for malware analysis. And then I will compare it to our approach, which allowed our team exceeded the Microsoft Malware Classification Challenge 2015 benchmark. Let me start by saying a few words about the actual status of malware. So the amount of unique malicious objects that were created is tremendous. Only last year, according to Kaspersky, over 24 million unique malware was detected. According to a report from IBM Ponemon, the average cost of the data breach in the UK is $4.88 million. So all of this combined with constantly changing malware signatures makes machine learning-based methods very useful because they offer very effective and fast detection and classification methods. Okay, so now I will talk about Microsoft Malware Classification Challenge. So in the 2015, Microsoft launched a challenge on the Kaggle website. The goal of this challenge was to classify malware into 9 families like adware, Trojan, or backdoor, based on file content and characteristics. Each sample malware had an ID, hash value, and an integer number, which indicates the class of malware. So we were given over 10,000 malware samples in training and tested each. Like I said before, there was 9 malware families and the total size of the dataset was around 500 gigabytes. For each malware sample, we were given 2 types of file associated with them. So we had hexdump, which you can see here, which is the raw data containing the hexadecimal representation of the file's binary content. And we had also metadata, which we can see here, which was generated by the interactive disassembler ADA Pro tool, which extracts information from the binary, such as function calls and strings. So the first type of file contains raw binary data in a hexadecimal format. So each line starts with an address, which tells us how far in the binary file we are and the binary data that are there. So here we can see a snippet of an assembly file. Each file starts with a keyword indicating a segment type, followed by an address and a sequence of bytes. So then we have an opcode and the operands. And the particularly interesting are the opcodes, as they are the actual instruction which defines the behavior of the malicious software. So static analysis is a process of analyzing malware binary without actually running the code. So the malware binary file can be reverse engineered by loading the executable into this disassembler, such as ADA Pro, and the machine executable code can be converted to assembly language code so that it can be easily read and understood by humans. And the dynamic analysis involves running the malware sample and observing its behavior in the system in order to remove the infection or stop it from spreading into other systems. So the system is set up in a closed, isolated virtual environment so that the malware sample can be studied thoroughly without the risk of damage to your system. In advanced dynamic analysis, debugger can be used to determine the functionality of malware executable, which otherwise would have been difficult to obtain using other techniques. Unlike static analysis, it's behavior-based, so it's hard to miss important behaviors. So one of the biggest challenge was to address the problem of overfitting due to highly imbalanced class distribution. So 3 methods were used depending on the type of data, starting from simple class weights, which affects the loss objective in the training phase, by proper cross-validation method, which fit equal number of samples of each class in each batch of data during a training phase, ending with the use of data augmentation, which allows us to unsample minority classes. So next, let me explain some of the terminology. There was 2 performance measures. The main metric that are used in literature when evaluating the performance of this benchmark are the accuracy and the logarithmic loss. So the latest is particularly important because it involves the concept of probabilistic confidence. So this is the cross entropy between the distribution of the true labels and the predicted probabilities. So now let me introduce you to the first placed solution of this challenge. So the future engineering and keyfold cross-validation played a key role in the winner's approach, helping them to prevent overfitting during future and model evaluations. They created 3 XGBoost models with different parameters and using different features in each model. Then they combined these models using weighted geometric mean to improve the accuracy of the final model. Also, they used a technique called semi-supervised learning, and they created pseudo-labels for the test set through the keyfold validation, and they train the model on the training and the test set together. So they generated the pseudo-labels for the test set and combined this test set with the training set. And then using keyfold validation, then they split the whole data set into keyfolds and train the model on the training folds and predict the labels for the test folds. And repeating this procedure key times, they generate the labels for all the test sets. So Microsoft does not disclose annotated testing results. However, even after the challenge, the Kaggle site, in response to a submission file, still returns the log loss. So it's interesting that although the number of scientific articles which cited the data set has exceeded 70, there are still no better results than those obtained by the winners. So now let's move on to the malware analysis with attention. So a model with attention learns to pay attention to relevant portions of the input that is processed. Thanks to the attention mechanism, we can get weight values for different words in a sentence, or bytes in bytecode, or opcodes in instructions in assembly code. And this works similarly in the human brain, where we also noticed some keywords in a sentence. And this is what makes the attention mechanism so successful. So here we see the hierarchical attention network that can be applied to the binary code in a very similar way to natural language processing. Each line of bytes corresponding to the opcode instruction can be seen as a sentence. So this way, using byte encoder and byte attention, we can build a representation of that sequence of bytes. Then we can aggregate those into a file representation using byte line encoder with attention. Okay, so using attention, we can find malicious parts in the binary code. We can find bytes in the lines with the highest weights, and they're related to the opcode instructions and operands. By determining such parts in the code, we allow the analyst to focus only on those parts instead of the whole file. This approach was used by authors of the article How to Make Attention Mechanism More Practical in Malware Classification. So they used the hierarchical architecture and achieved poor results. Additionally, they tested other architectures with attention. Then they combined the attention mechanism with convolutional layer, and the best result they obtained was an accuracy of 96.09%, which is not satisfactory. Also, the choice of the kernel size was completely unjustified. So right now, there is currently no architecture suitable for malware that could outperform classical methods like attention did in the NLP field. So this leads me to my next point, where I'm going to tell you about the approach that me and my team came up with. So in our work, we analyzed various methods used so far in the literature and used them as a basis of our extension. So there was CNN plus LSTM neural network, which used convolutional layers, followed by LSTM layer with, but there is a lack of word embedding or one-hot encoding. The LSTM neural network consisting of the LSTM layers, the metadata features, which we selected 18 features from the whole over 300 features using random forest algorithm with Gini criterion, and the engrams. So our original results use word embedding and one-hot encoding. The first two models takes as an input binary sequence of data. The third model, gated CNN, takes as input the sequence of opcodes from assembly file. So the first model, malconf LSTM, which used word embedding and gated convolutional layers with large filters of size 500, followed by the LSTM layer and the fully connected layer. The second model, CNN plus LSTM plus batch normalization, used word embedding with convolutional layers and batch normalization layers, followed by LSTM and fully connected layers, and the gated convolutional neural networks, which used one-hot encoding. So all the calculations were done on two large servers with NVIDIA cards. And here we can see the results of our implementation of various neural networks methods. So they are mostly better than corresponding implementations in the literature. Especially interesting is the fact that none of the neural networks architecture are really close to the best solutions of the challenge. And in addition, the models that have achieved the best results are those with the input of binary data. Okay, so the standard way for counting engrams is very memory consuming. Therefore, many approaches used in the literature consist in limiting the set of engrams to a much smaller number. So this most often involves selecting the most frequent engrams. And this is a different approach compared to heuristic in text information retrieval, where TF-IDF procedure is used. Besides that, commonly InfoGain is used to select engrams that carry the most information, and this way we can decrease the size of features even more. Okay, so we expanded the approach of the winners of the challenge using also 6 and 8 grams for binary code. So the use of 8 grams is completely novel. We used XGBoost classifier. Here are the results for those engrams created from opcodes and bytes, binary code. So engrams from binary code give better results compared to engrams from assembly code. And the best result was obtained by combining all those engrams. And finally, we proposed an ensemble architecture. So a general procedure of stacking ensemble method involves a learner trained by to combine other heterogeneous learners results. So the individual learners are called the first level learners. And that learner, the ensemble learner, stack the output of the first level learners for making a better predictions. So the basic idea is to train the first level learners using the original training set, and then use their output to generate a new data set for training the second level learner. So each first level learner provides 9 features because there was 9 malware families, 9 classes, and we combined those outputs from our models to extract a lot of useful informations from various types of data. And we combined all the neural networks model, the metadata XGBoost model, engrams features from for assembly and bytecode, and also the first place approach models using the ensemble classifier. So we tested 3 different second level learners. So there was multinomial logistic regression, extreme gradient boosting classifier known as XGBoost, and weighted geometric mean. So the weighted average ensembles allows the contribution of each ensemble member to a prediction to be weighted proportionally to the trust of performance of that members on the test set. So the weights were selected as the inverse of the log loss result obtained from the validation. In this way, better performing models are given greater importance. Okay, so using the ensemble of our approach, we are able to obtain the best log loss result so far, which is 0.0025, and the validation accuracy is very high, missing only 2 samples. Still, there is not clear why advanced neural networks, such as successful in the natural language processing, achieves poor results compared to classical methods like engrams. Maybe the dataset is too small, or used neural networks are not sophisticated enough. Maybe the malware has very different semantics compared to natural language. Maybe increasing the length of the engrams to large numbers like 10 could improve the result. So we combined the winning approach of the Microsoft Malware Classification Challenge with the neural network approach. And mixing those approaches, we're able to get the best log loss result so far in this challenge. And this mostly comes from the XGBoost model with the engram contribution from binary and assembly code. And additionally, we discovered the error in the say no to overfitting team, the first team, and enhanced the method by including 6 grams and 8 grams. And still, it's not clear why adding 6 gram to binary code analysis does not improve results, and adding 8 grams only improves the results a little. So despite the impressive result, still there is no full understanding why the pure neural network approach is still not satisfactory. In our opinion, the classical approach, increasing the length of the engrams up to 10, should improve the result. And the engram selection should be improved through engram TF-IDF. And most important, the current malware classification using attention type networks as applied in the literature does not provide good results yet. But we are in the process of computing of more advanced attention type neural networks and reading the current limitations. Okay, so thank you very much for your time. If you have any questions or comments, feel free to ask me now or contact me later through an email or ping me on LinkedIn. Thank you.
Thank you, Piotr, for this very interesting presentation. I must admit that rarely I see assembly code on the machine learning presentation. It was a bit scary, but also refreshing. I remind our participants that you can ask questions to Piotr on our Q&A tab. The approach is quite complex. You have a lot of different elements of it. So I would like just to ask some maybe clarifications, clarification question. So you have mentioned, for instance, data augmentation, which I think can be kind of difficult in assembly codes and, let's say, malware. So maybe can you comment more on that?
Okay, so this data augmentation procedure was very interesting in my opinion, because we used this procedure on a sequence of opcodes in assembly file only, and so the sequences of the opcodes in those files are very long, and they are hard to calculate using, for example, neural networks with LSTM layers. So the approach was to split these long sequences into shorter sequences of the length of 120. So, for example, we split the sequence of the sample of a malware to shorter sequences, and train the model to classify a sample using only one short sequence, and this way we obtain the model that could provide us a result for short sequences with some probability, and we could use those probability to filter out sequences that were predicted with a low score. So for example, if this subsequence had a high probability for some class, we use those sequences. So if we split a long sequence to short sequences, we can split them just using a window of a fixed size, but we can set a step for that window. So moving that window with a fixed step, we can split the sequence to we can modify the number of subsequences which we can obtain from this long sequence. So calculating this step of the window, we could set the number of subsequences that we can obtain for each class. So this way we could have an equal number of these subsequences for each class, and that was the data augmentation we use.
Thanks. You've also mentioned like one model who has had like 96 something % of accuracy, and you commented that it's insufficient. So
yes, so in this competition there was an easy way to obtain such accuracy because using such a simple features like 1 byte engrams or even only counting the numbers of the length of each sections in the disassembly file, using only those simple features, we were able to achieve the accuracy of 97 or 98 even. So the problem in this competition was to fight the overfitting problem due to this imbalance data set, and so
Sure,
that was the problem, and the accuracy of 96% is really poor.
Okay. I think that we have run out of questions, and also it's already the time for the closing session. So thank you very much.